O2I Institute, and today we're going to be learning about something new named geometric sequences in series. So we've already learned about arithmetic sequences in series, and they all have a common difference. And lucky for you, geometric and sequences in series, they don't have a common difference. But instead, there's something to replace the common difference, and it's called the common ratio. Now, the common ratio is actually pretty easy to comprehend. I'm sure you've all heard of ratios before. A ratio is just the proportion between two numbers. So for example, the ratio between 1 and 3, it's 3. The ratio between 2 and, say, 12, it's 6. Easy enough. Let's get into an example of a geometric sequence. So this would be an example. And we can see that there's clearly no common difference. The difference between 2 and 1 is 1. The difference between 4 and 2 is 2. They're not the same. But if we divide 2 by 1, that's 2. If we divide 4 by 2, that's also 2. So there is a common ratio of 2. Now let's look at some more examples. So this will be another example. We can see that there is no common difference, but there is a common ratio. And here's another example. Now try to find the common ratio of the last two by yourself. And pause here. Okay, so here's the answers to them. So the common ratio of the second one is 3, and the common ratio of the third one is 4. And here's their leading terms, because they will both come in handy. So now let's get into the first formula. And as we can see, A here is the leading term that we guessed that would be used. And R here is the common ratio that is also being used. But what is going on with the n-1 exponent stuff? Well, let's figure it out. I'm going to take the most basic geometric sequence. 1, 2, 4, 8, 16, 32, and so on. There's infinite terms. So 1 here is our first term, A. And 2 here is our first term times the ratio, which in this case is 2. So AR. And then 2 times the common ratio 2 is 4. So A. It is not 2R in this case, but R squared, because we're doing multiplication instead of addition. Now this would be A, R to the power of 3, and so on. AR to the power of 4, AR to the power of 5. And we can see that this is the first term, this is the second term, third term, fourth term, fifth term, sixth term. Can we see any relationship between these exponents and the position of the term? The exponent is the position of the term minus 1. So that's where the n-1 comes from. So we get this formula. In the next video, we'll go over some other formulas for finding the sum of geometric sequences.